basically just start into with balancing equations, which we certainly are experts at this point. So what I want to do is give you an equation to balance, and hopefully I fixed the function in here where you can answer the questions. I think the problem was last week when I put a poll in there. There are too many questions on it, so I've separated them out, and I'm crossing my fingers it's going to work this time. Basically, you know how this works. We balance a chemical equation. We have to remember there's two things we need to balance. We need to balance the atoms on both sides, and by doing that, we balance the mass on both sides. So we can actually use both those pieces of information to figure out balanced equations sometimes. If we're given two masses of reagents and one of the masses of a product, we don't actually have to go through figuring out all the moles and everything else. We can just, as long as we have a balanced equation, and that is the key, as long as we have a balanced equation, we can figure out the total mass of the products has to equal the total mass of the reactants. That's always going to be the case. And one thing that's going to be really important as we go along is specifying the states of matter, as is written down here. Because you've seen it's going to be really important when we're talking about reactions that happen in solution. Some things are going to remain in solution, and so we'll say they're aqueous. They don't necessarily have to be ionic. For instance, sugar dissolves in water, and it's not ionic. So we would say that it's dissolved. It's aqueous. But you remember when something is no longer soluble in water, and we're going to go into that in a lot more detail than we have before, talking about what are some of the rules other than strictly things with a lot of ionic charge tend not to be soluble, which is still true, but there's also some other things to look for. When they fall out of solution, then of course they become solids. And when they become solids, they no longer are reacting in the solution like they were before. So if we had, say, silver ions, which were involved in some sort of reaction, once those silver ions are converted into the solid, they're basically taken out of the reaction. And so it's important to know which parts are remaining in solution and which parts aren't. So here is your question. I'll see if I can get this to work this time. So we're going to go through a lot of the different types of reactions. You know, this is a combustion reaction. You're also going to find out in this chapter that it's a redox reaction. It's a redox, meaning reduction and oxidation. Electrons are transferred from some atoms to other atoms. That happens very, very rapidly in a combustion reaction, as you can probably imagine. So what I'm going to do, hopefully, is put the poll in. Here we go. And give you 5 minutes to figure out if you can get this one right. And then we'll go over it together. So have at. If you have any questions, let me know.
Yes, sorry, Professor, we're balancing the equation first?
Yes. Yeah, balance, adjust the coefficients, make sure they balance. And of course, the states of matter here are given for you, so you don't have to worry about that. And what do you got in there quick? Probably because you figured it out from last week. You okay?
Yeah.
You can sneak in and say hello, right? That's my sweetie. All right, got about a third of you in here already. Excellent. So does everyone have a little notepad next to their computer? I definitely do. See if people remember the trick in doing these. We sort of went over that before. There's kind of a mean trick. Now we got 5 of you left. All right, 3 people. Got about a minute 15. All right, man, you last 3. Either you're stuck or you're just not playing along. Okay. Let's go through it. You see, most of you got it right there. So the key to doing these combustion reactions is to realize that oxygen is going to be in both the products. And the tricky thing is there's going to be only one molecule of oxygen in water, but there's going to be 2 in carbon dioxide, which means there's going to be an even number of oxygen molecules on the left and an odd number of molecules on the right. So that automatically creates some issues sometimes. So the way to get around that is to not worry about oxygen until you've balanced everything else. So the first thing to do is balance the carbon, and that's pretty straightforward. 18 carbons, we're done there. Then we do hydrogens next, 38 of them. And then there's 2 over there, so half of 38 is 19. So that's 38. Now we figure out, now that we've got our hydrogens balanced and our carbons balanced, we balance the oxygens last. So here we have 19 And here we have 18 times 2, we got 36 for a total of 55. So there's 55 oxygens. Problem is, we've got 2 on the left side. So what do? We cheat and we say there's 55 divided by 2. Rather than think about this in terms of molecules, we think about it in terms of moles. We can't have 55.5 molecules. We can have 55.5 moles, however. So we say that there's 55 over 2 moles. Now that we realize, let's go back to molecules. We can't have 55.5. So what do? Multiply everything by 2. So we multiply this by 2, we multiply this by 2, we multiply that by 2, and we multiply this by 2. And we're left with 2, 55, 38, and 36. So that's basically how we go about with that. Most of you got that one right. Great job. Next thing we sort of, a lot of people had trouble dealing with the idea of limiting reactant when that came up in chapters 2 and 3. Because usually when we're just sort of balancing equations, we just figure, okay, I have this much, like in the last example, I have this much of the thing I'm burning. I have this much oxygen to burn it with. They completely balance out, and I get so much product. But that almost never happens because it's very, very difficult to get exactly the right amounts of each reactant so that they completely react with each other and leave nothing left over. That rarely happens. And so what happens quite frequently, as you know, is that one reactant is going to be in a higher concentration than the other. Not only a higher concentration, but be in excess of what is required. So one reactant, oops, let me go back. There we go. So what's going to happen is one reactant actually limits the amount of product, because by definition, when that reactant runs out, no more product. Because we need both reactants. Like for instance, in the last reaction, we have the hydrocarbon and we have the oxygen. Well, if we were burning that in, let's say, a closed environment, once all the oxygen is consumed, fire goes out, right? I mean, that's how fire works, basically. Once the oxygen has been removed from the reaction, no more fire. Same is true if we were if we were burning it in an open container. Once all the hydrocarbons used up, no more fire. So the limiting reaction is the one responsible for determining the amount of product, because it limits the amount of product and it stops when it's all gone. Therefore, by definition, if something is limiting, something is also in excess. Or when they're balanced completely, both are limiting, because each of them determines if I have exactly the right balance of oxygen and hydrocarbon. Once they're both used up, then I'm finished making product. But in the situation where one is in excess, one is limiting, the other one by definition is in excess. So that's going to be left over. And we determined those amounts in terms of moles. So we'll go over, I'll introduce this one, and you guys can work on it and see if you can get it. So I think we sort of left it here last time. So early days of rocketry, fun, lots of missing fingers and hands. You had 2 liquids, very unstable liquids, not to be toyed with. So we have one called hydrazine. It even just sounds dangerous, right? Hydrazine sounds like it's going to explode on contact. And it does when it comes into combination with the second liquid, dinitrogen tetroxide. And so what's the very first thing we need to do when we have a problem like this? Because it's asking us a couple questions. How many grams of nitrogen gas form, and how many grams of the excess reactant remain when the reaction's over? What's the very first thing we have to do in this situation before we do anything else?
Balance the equation.
Bingo. Yeah. We don't even know what the reaction is at this point. We just have two reactants and we say, yeah, they react, and then something's made. We know that one of them is nitrogen gas. We don't know what the other one is. So we have to figure that out. So that's going to be our first step. So let's do that. So I've got N2H4. That reacts with N2O4. And what do you think my products are going to be? One of them is nitrogen. What do you think the other product is?
Water.
Yeah, exactly. Because we have hydrogen here, we have oxygen here. Generally, when you have hydrogen and oxygen reacting, oxygen's going to grab those electrons from the hydrogen and make water. So that is going to be our other product. So we need to make sure that this is balanced. So looking at it right now, nothing is balanced. Oxygens aren't balanced, nitrogens aren't balanced, hydrogens aren't balanced. So let's balance the hydrogens. Let's balance the nitrogens first, I guess. Actually, we can do that last. Let's balance our hydrogens and oxygens, and then we'll deal with our nitrogen at the end. So hydrogen, how do we balance that? Give us a little.
Multiply 2 on the right side for the hydrogen to give us 4 hydrogens on each side.
Yeah, put it. Oh, hydrogen. Sorry. Oops.
Or are we doing hydrogen first?
Yeah, I think that's probably the way to go. So yeah, so that gives us 2 waters. Then we need to balance oxygen. So we probably need to double that, right? Because we have 4 oxygens here. We have only 2 here. So why don't we double the amount of water? Does that seem reasonable?
Yeah, so sorry, I'm just confused. So if we doubled okay, never mind. Sorry, it's early. I see it.
Yeah. So we double the water, so we make 4 instead of 2. That gives us 4 oxygens here. And it gives us 8 hydrogens, so we just put a 2 there. That balances that. And then we leave nitrogen for last. And how many total nitrogen atoms do we have as reactants?
8.
8?
6.
6. We have 4 here and 2 here for a total of 6. So how do we balance that? How am I going to balance my nitrogens now?
Are we adding a 3 in front of the nitrogen on the right
We
side?
could do that. That's probably not a bad idea. Let's do that. 3. Right, so our final, so that gives us, I think that balances everything. So let's write that out. So that gives us, so we're going to need this to do our equation. So we have 2 N2H4 plus into O4 gives us 3, oops, let me go back. What the hell's going on here? Here we go. 3 nitrogens and was 4 waters, right? Yeah. So there's our reaction. So you can see, actually, if you look at, if you assume that all of these are going to be gases, and they will be, or these are liquids, and these will be gases. You can see how that takes a very, very small volume of liquid and turns it into a large volume of gas. That's why it's such a good rocket fuel, because it propels, you take, 3 moles of liquid and convert it into 7 moles of gas. So you get this huge expansion. So it pushes this thing along. So let's do the first one together. So how many grams of nitrogen gas form when you have 100 grams of hydrazine? So we have 100 grams of hydrazine, and we have 200 grams of dinitrogen tetroxide. So what do we do now? How do we, and what we want is how much nitrogen. So what do we do in this sort of situation? So now we have a balanced reaction. Always job one, getting our balanced reaction. What do we do next?
To see which is excessive, which is limiting.
Not yet. That's further on down. That's further down the line. What's the very next thing to do?
Convert it to moles.
There you go. Yeah, because we need moles, because, as we always say, reactions don't happen gram to gram. They happen mole to mole, molecule to molecule. So we need to convert everything to moles. So how many moles of hydrazine do we have here? So N2H4, how many moles of hydrazine do we have? How do we figure that out? So we have 100 grams times something. What are we going to multiply that by to give us moles?
The molar mass.
So what do we do with the molar mass? We definitely need the molar mass. You're absolutely right. But what do we do with it?
We're gonna put 100 grams times 1 gram over the molar mass of sorry. I was sorry, I got confused. I was doing one at a time.
Now remember, the molar mass has a division right in there for us, because it is grams divided by moles. So it already is doing the division for us. So basically all we need is that number, and then we put the units in there. Because remember, I always want you to have the units when you do these calculations, because it will steer you in the right direction. So let's say the molar mass, so there's two, what is the molar mass of N2H4? You don't have to have it like super precise, but like, or you can just Google it. What is our molar mass?
32.04.
Okay. What, 32.04 what?
Grams per mole.
There you go. So 32.04 grams per mole. So when I take my 100 grams and I multiply that by something, what am I going to multiply that by? Where do I put my 32 grams, or where do I put my moles?
32.04 gram under and 1 mole above.
Right. So that way my grams cancel out and I have my 1 mole up here. And that gives me the number of moles. Exactly. So how many moles is that?
That is 3.1205.
0.120 moles. Okay. So now we know how many moles of hydrazine we have. Here, let's see if I can move. Let's get a different. There we go. There we go. That's what I was looking for. Okay. So we've got let's put our balanced reaction up here. So we've got 2 and 3 and 4. And we figured out we have 3.120 moles of hydrazine. Now, what's the next piece of information we need? What other piece of information do I need to continue?
Yeah, more of the N2O4 if 200 grams are used.
Right. So we need both. We need both moles. We don't know at this point which one is limiting. It could be that hydrazine is limiting. I don't know. But we need to figure that out first. In order to do that, we need to figure out how many moles of each one we have. So I've got 200. Oops. I've got 200 grams of N2O4. I'm going to multiply that by something to give me moles. So N2O4, how many moles of that do I have? How am I going to, what do I plug in?
92.01 grams per mole.
And what do I do with that information?
Put the 92.01 grams under and 1 mole above.
So was it 92.01?
01.
Right. So that way I cancel my grams. I'm left with moles, which is what I want. So how many moles is that? A little over 2 by the looks of it.
2.174.
Okay. So at this point, how do we determine which one is limiting? Anyone remember how we do that? How do we determine which one is actually the limiting reactant? Because we probably can figure out at this point that they're not balanced
Divided
perfectly.
by the smallest.
Divide what by what?
Divide both of them by the smallest, the smaller one.
I don't understand what you mean. The smaller one of what?
3.120 divide 2.174 and 2.174 divided by 2.174.
What does that give us though? What information does that give us?
Well, let me see. The ratio.
Okay. But is that the right? But does that give us the ratio that's actually going into that's used in this reaction? What's the ratio used in the reaction? Oh man, Mavlan is way ahead of us here. There's actually one very simple, straightforward way to figure this out.
3.120 moles divided by 2, that is less than 2.174. one.
No, we don't even need to do that. There's a much simpler, more straightforward way to think about it. Because if a reagent is limiting, that means it limits the amount of product. And so the question was about how much of this product are you going to make? Like how much N2? And we can answer that right now. So what do we do to figure out how much N2 is made? We don't have to go here and figure out what the ratios are between these two. What's more important is what's the ratio of reactant to product. That's the key. Which one makes less product? That is the definition of the limiting reaction. So if we do that, we take our 3 moles of hydrazine and we convert that to product and see how much it is. We take our little over 2 moles of dinitrogen tetroxide, convert that to product and see how much that gives us. Whichever one is less, that's your limiting reactant. So which one makes less? And it also answers the question for us, how much N2 is made? See, that's the advantage of doing it that way. It kills 2 birds with 1 stone. 1, it tells us which one's limiting. And 2, it tells us how much product is made. So how do we figure how much product is made from 100 grams of hydrazine?
The ratio, the molar ratio is 2/3.
Right. What we want to do is convert hydrazine to nitrogen. And we do that in terms of the balanced reaction. So I have moles. I start out with my moles of hydrazine. And I'm going to divide by moles of hydrazine. How many moles? 2, because that is from my balanced reaction. How many moles of product am I going to make? 3. That's from the balanced reaction. So for every 2 moles of hydrazine, I make 3 moles of nitrogen. I cancel out moles of hydrazine, and what I get is moles of nitrogen. So how many moles of nitrogen is that?
3.12. That is 4.68 moles of nitrogen.
So that gives us 4.68 moles of N2. Now we do the same thing with N2O4. Whichever one is smaller, that's how much we're going to get. So I've got my 2.174 moles N2O4. So I want moles of nitrogen. Again, that's going to be 3. 3 moles of nitrogen on the top. How many moles of N2O4? 1. Cancels out my N2O4, leaves me with moles of nitrogen. How many moles of nitrogen is that?
6.522 moles of nitrogen.
So which one is limiting?
The nitrogen.
Hydrazine, right. Hydrazine is limiting. So we've answered 2 questions. We know which reactant is limiting. It's the hydrazine. And we know how much product is going to get made. That much, that many moles. So if the question was how many grams of N2, we just take our 4.68 moles of N2. We just do a moles to grams conversion. So what do we put in? I want to be left with grams of N2. What do I multiply my moles by to give me grams?
28.014 grams per mole.
What? That's the. Was it 28 point?
0.01 grams
Is
per
that for nitrogen or for N2?
Not N2.
N2, right. So one mole of nitrogen N of nitrogen atoms. That's also a way to get mixed up here. We're not dealing with nitrogen atoms. We're dealing with nitrogen molecules. We've done nitrogen enough with Lewis dot structures. We know it's N2 by now. So where do we put grams and where do we put moles?
Grams per mole, grams above.
So it cancels my moles. I get grams. How many grams do I get?
How many significant figures was it? 3?
3.
It's 131 grams.
131 grams. So we did that part together. The second part I want you to work on. The second part was how many grams of the excess is left over. So the excess is the dinitrogen tetroxide. And the question is, how much do we have left over? So I'll give you a couple of minutes and then we'll do that one as well. All right, see if I can put this. See if I can. There we go. So you got four answers there. Of course, kind of gave it away with the because we know it's not hydrazine, it's not going to be excess. So So think about how you would do this. Basically, what you want to do is go in reverse. We figured out which reactant was limiting by figuring out how much product we would get by completely using up the reactant. Now, basically, we're going in the opposite direction by taking how much product we have and then reverse engineering how much reactant we must have used to make it. That's how we approach questions like this. And so we're interested in how much dinitrogen tetroxide was used. How do we figure that out? By how much product was formed. That will tell us how much was actually consumed. And then we can figure out how much was left over. Oh, slowly but surely, getting more and more people in. Everyone's getting it right. It's very good to see. All right, one more minute. We'll have a look. Oh man, is it pouring down rain where everybody is right now? Started really coming down. All right, time's almost up. All right, so you can see most of you, almost everybody got that one. So to do this, we take advantage of the fact that we have information that we can use from our last calculation. So our last calculation told us how many moles of nitrogen we're going to form. It was 4.68. So we use that information to go backwards and figure out how many moles of N2O4 must have been made. Rather than just take that information and say, well, how many moles of N2O4 must have been used to get that? What's the ratio between them? Well, we know that it's 1 to 3. So if 1/3 of the number of moles of nitrogen are moles of N2O4 being consumed. So we take the number of moles of N2, it's 1 N2O4 over 3 N2. That gives us moles of N2O4 that were used. And that is 1.56. So we just convert that to grams and then subtract that from 200. And that gives us our grams of excess left over. Okay? All right. 56.1. Another thing we dealt with previously was looking at yield. And if we were meeting in the lab, we would have dealt with this a lot more, actually, because you'd be doing actual chemical reactions and then measuring the amount of product you got. And so you will find that the actual yield, as it's stated here, I wouldn't even say almost always. I would just put the always. It's basically always less than 100%. And that's no fault of the people doing the experiment. Some of the product just isn't going to form. Some of the, for instance, elevated temperature may be required to get the best reaction going. A lower temperature may be required to get the best yield going. It may take months for the reaction to go to completion, and you don't have that much time. But the usual thing that is the culprit in yield is you lose some by recovering the product, because basically you rarely, if ever, get a pure product. Because remember, unless your reactants are completely balanced perfectly, what you're going to get at the end of the reaction is going to be your product and excess reactant and water and whatever else is there. And so in order to figure out how much product you have to remove the water. And well, you say, well, that's easy. You just dry it. Well, how long do you dry it for? It may take, a really long time. You may want to heat it in an oven to remove the water. Well, what if that you lose some of the product by doing that? Maybe some of the product turns into vapor when you do that as well. You also have to remove the excess reactant. And so by removing all that other stuff to get to your pure product, you lose a bunch of it. And so, that just comes with the territory. So if you can get a yield of more than 50%, you're generally pretty happy. And I may have mentioned this before, for those of you who want to become like chemical engineers, this is one of the main problems that chemical engineers deal with in an industrial sense. Because when we're in the lab, messing around with chemicals, they're not going to be very expensive or anything like that. And if we lose, if we lose a couple grams of sodium chloride, no big deal. But if you're synthesizing something on an industrial scale with kilograms, and maybe thousands of grams, or hundreds of thousands of grams, if you can twist that to get just even a couple more percent yield, you're going to be saving your company potentially millions of dollars. And so yield is a huge thing for chemists, especially in industrial chemists, to deal with. So what is the problem? So this is one industrial reaction right here. It's basically, you take two very cheap things and you combine them to make something very valuable. So silicon carbide is really valuable because you can make, it's incredibly hard. Pretty much anything that's carbide is incredibly hard. And so you can use it as an abrasive, you can make sandpaper out of it, you can make all sorts of things out of it. But you can see it's a really simple reaction. You just take sand, and that's pretty cheap, and you take powdered carbon or graphite, and that's pretty cheap too. You mix them together at very high temperatures, and you get the reaction taking place. So the question is, if I have 100 kilograms of sand and I recover that much silicon carbide, how good of a process is that? What's my percent yield? So what's the very first thing that you do to answer this question? What's the first thing we need to do? How do I go about answering this question? There's a lot going on here. So I need to break it down. What's the first step in answering it?
Balance the equation.
Yeah, I got to have an equation. I don't even know what the reaction is yet. I mean, basically, I have my two, actually I do have what's the necessary ingredients. I have my two reactants and I have my two products. So what are my two reactants? Right, so we need to have
dioxide and carbon.
Right, so I have silicon dioxide and carbon. What do I put down for carbon? So silicon dioxide is a solid, obviously. What do I put down for carbon? Just C? Was it C8 or C6? I mean, what do I put down for carbon?
E. C.
Just C, right. Just carbon. So that is just the formula for graphite.
Or C infinite.
That's it. Right, because I mean it's all connected, but we don't know what the connections are. But if you just put down carbon, moles of carbon. And And what are my products? Those are my two reactants. What are my two products?
Carbon monoxide and silicon.
Silicon carbide is
Carbide.
one. What's carbon monoxide? What's the formula for carbon monoxide? So before I can write down carbon monoxide, you have to tell me what it is. How do I write it down? Right. CO. So that's where we start. So we have sand, silicon dioxide, and carbon. And from that, I make silicon carbide and carbon monoxide. Okay. So here's our reaction. So next, we have to what? We have to balance it, right? So how do we balance this reaction?
Wait, 100 kilograms sand, not 100 kilogram of
That is sand. Silicon dioxide
pure
is
silicon
sand.
dioxide.
Yeah,
Okay.
that's what sand is made out of. I mean, obviously, there's other impurities in there. I mean, it's a naturally occurring mineral, so there's going to be all kinds of other stuff in there. But for the, for the sake of argument, we'll say that it's pure silicon dioxide. It's mostly silicon dioxide,
Okay.
like 95 to 100%. But it's not absolutely pure. There's going to be other minerals and stuff in there. So I need to balance this reaction. So how do I go about balancing it?
I would first add 2 coefficient to the right side of the carbon monoxide.
Yeah, I got two atoms of oxygen in the dioxide, and so I'm going to need 2 on the right side as well. So that balances my oxygen. My silicon is balanced. What about my carbon now?
Carbon is 3 carbons.
So I've got 2 in carbon dioxide. I've got 1, so I want 3.
So someone asks in the chat that why is it not carbon dioxide?
Oh, that's just the reaction that takes place. I think it's because of the very high temperature. Just because of the very high temperature, I think it limits the oxygen and carbon, and you have an excess of carbon over oxygen. And so when that happens, I mean, there's more carbon in this reaction than there is oxygen. And so when you do that, basically you're limiting the amount of oxygen that reacts with carbon. And so you get carbon monoxide as a product rather than carbon dioxide as a product. It's because of the molar ratios. Yeah, so does that balance? I think that does balance everything, right? 3 carbons, 1 silicon, 2 oxygens. Yeah, I think we're set to go. So the question is, what is the yield? What's the percent yield if I get 51.4 kilograms of product? How do I figure out, that's the actual yield. What do I need to figure out to get the percent yield?
We need to calculate the theoretical yield.
Exactly. How do I do that? And before, what does that mean, my theoretical yield? You're absolutely right. But what does that mean?
means like what we calculate to be the yield, like the maximum possible.
There you go. Right, exactly. If everything went perfectly and I was able, it reacted completely and I was able to recover 100% of the product, how much product would I have? Precisely. So what is going to be our theoretical yield? Our theo yield, what is that going to be? How do we figure that out? Because remember, this theoretical yield of silicon carbide. We're not interested in the carbon monoxide. That's basically a waste anyway. And we don't really need to, since this is a solid and this is a gas, it's going to be pretty easy to separate. So what is our theoretical yield of silicon carbide? How do we determine that?
By the balanced equation.
So where do we start?
We convert silicon dioxide into moles.
Right. So we take silicon dioxide, that's silicon. Silicone's a whole other thing. Silicon dioxide. So we have 100 kilograms of it. How many grams is that? How many grams? If I have 100 kilograms, how many grams is that? Yeah. It's just multiplied by 1,000, right? Exactly. So we have 100,000 grams. Now I need to convert that to moles. How am I going to get moles? How do I get moles of silicon dioxide?
Multiply 1 mole over 60.08 grams.
So 1 mole of silicon dioxide is 60.08 grams. So I cancel my grams out. How many moles? That's going to be a lot. How many moles is that?
Uh, 1664.447.
1664. 1664 times point something.
447.
1664, like 0.5. Is that close enough?
Yeah.
Okay. So that's how many moles of reactant we start with. How many moles of product are we going to get? So if that's how many moles of silicon dioxide we get, how many moles of silicon carbide do we wind up with? So we have this many moles of silicon dioxide. How many moles of product do we get?
The same amount.
Why the same amount? Same amount of grams, same amount of what?
The same amount of amount.
Same amount of what? We need to have same amount of moles, right? We need to have a unit, same amount of something. So we get the same amount of moles, right? Because it's a 1-to-1 ratio. So however many moles of silicon dioxide I have. Just notice there's basically 1 mole of silicon goes in, 1 mole of silicon comes out. just in a different form. So now I get 1,664.5 moles of product. Now it's just a matter of figuring out how many grams that is, because generally when you're measuring something, when you're measuring product, you generally don't measure it in moles because you don't weigh moles, right? You take the mass of something. That's the easy thing to do. So we generally need to figure out what our mass would be of product. So we need to convert 1,664.5 moles of product into mass. So what's my mass of silicon carbide?
.096.
So silicon carbide is 40.0. What is that? What are the units we're talking about?
Grams per mole.
Okay, so now I want to take moles and turn them into grams. So where do I put my grams? Where do I put my moles? So we're going to multiply my moles by something. Where do I put grams? Where do I put moles?
Grams above.
Right, grams on top because I want to be left with grams. So grams go on the top, moles go on the bottom. And 40.11. So how many grams is that?
That is 7.1.
Sorry, what is it?
6676.1.
6676.1.
63.1.
I'm sorry?
6763.1.
6763. Oh, okay. Six, 763.1 grams. So that's our no. Okay. Maybe just put it in the chat. I could read it.
Okay.
There we go. Okay. So that is in grams. We're given our actual amount in kilograms. That's a pretty straightforward conversion, right? We just go 1, 2, 3, because there's 1,000. So our expected yield is 66.76 kilograms. So what is our percent yield? This is our theoretical. This is our actual. What's our percent yield?
.77.0%.
Where does that come from? How did you get that?
51.4 kilograms over 6673.1 kilograms.
Mm-hmm.
And
that gives you 0.077
770. Yeah, 0770.
Now remember, when you have percent, that means out of 100. That's what percent means. So we just take this fraction and multiply it by 100. And since we have 3 significant digits, our answer is 77%, which, yeah, 77%. All right, so our limiting reagent, that's the one that's completely consumed. Theoretical yield, the amount of product that you could make if you got 100% of the reaction took place and you recovered 100% of the products. And then your percent yield would be whatever you actually got after your reaction and recovering the product divided by the theoretical times 100. So one thing we did early on, I think you guys did a really good job with, is determining empirical formulas and molecular formulas. And we did that, if you remember, way back, by looking at the percent composition. And percent composition was just basically out of the mass of our product, how much was sodium, how much was oxygen, how much was carbon, how much was hydrogen, and so on. And so you take those percentages and just convert them directly to mass. And the easiest way to do that was just assume we had 100%, 100 grams of sample. That takes my percent and immediately changes it to grams. Now I have a mass. That's something I can use. So then you take those masses, convert them to moles. Now I have a ratio of moles. And that basically is what a formula is, right? It just tells us how many moles or molecules, depending how you want to look at it, how many moles of each atom is in a mole of the product, your formula, whatever the molecule is. Divide each number by the smallest number of moles because we want whole numbers. Very rarely we're going to get whole numbers, right? We get all sorts of weird fractions and everything, but we want whole numbers when we do a formula. And so to get a whole number, we multiply to give us the smallest whole number ratios. So let's do a quick one together. When we can probably figure out what it is right away. So probably familiar with this reaction. You ferment grain, you make ethanol. So when you ferment something, basically what that means is you're breaking it down and producing another molecule. So what you're doing is you're taking the carbohydrates in the grain. Carbohydrates have a formula that looks like this. Carbohydrates have carbon, hydrogen, and oxygen in them in varying ratios. The most simple one we know of is one of them is sucrose, C6H12O6, so table sugar. So you ferment that, you turn it into ethanol, which is C2H5OH, and it releases a gas also. And if anyone's ever brewed beer, you know which gas I'm talking about. And it has this percent composition. That much carbon, that much oxygen. So how do we figure out what that gas is? So what's the first thing? So here's, basically this is the information we're given. That much, so if I have a certain sample of this gas, and remember, this is always by mass. That's really important to remember. It's not by moles, it's by mass. So around 27% of the mass is carbon and 73% of the mass is oxygen. So what do I do with this information? Because at the end of the day, I'm going to want moles out of this. So where do I start with percents?
We convert them into grams by dividing them by 100.
Yeah, convert it into gram. Yeah, I can't do anything with percent. That doesn't mean anything. But I can convert it to grams if I assume if there's 100 grams of the total, whatever this is, if I have 100 grams of it, then I know I've got 27.29 grams of carbon and I got 72.71 grams of oxygen. Now I'm getting somewhere. Now I have a mass that I can work with. What's the next thing I need to do? Do I just divide 72 by 27 and see what the ratio is? What do I do? Right. Converted both to moles. How do I do that? I need moles of carbon and I need moles of oxygen. How am I going to get them? Yeah, so I want moles from both. So I put moles, when I do my conversions, I put mole on the top. Now 1 mole of carbon is, right, 12.0. That's the easiest conversion ever. You just look it up on your periodic table that you have tattooed on your forearm. And so how many moles of carbon is that? .27, man, good job. 2.27 moles of carbon. How many moles of oxygen do I have? So 1 mole of oxygen is 15.999 grams. One of those things that's burned into your brain after a certain period. How many moles of oxygen is that? Another thing to remember when you're doing these, usually when you say moles of oxygen, we're talking about oxygen, O2. But in this situation, we're talking, notice that we don't have O2 here. We have just oxygen. So it's grams of oxygen atoms and grams of carbon atoms, not molecules. So that's an easy mistake to make. So we have 4.54 moles of oxygen. So here I've got two numbers that don't, I've got with odd fractions left off. So I can't have that. So what do I do in order to get whole numbers? Because I can't write a formula C 2.270 4.54. That's not a formula. I need whole numbers.
You can divide both by the moles of carbon, since
Right, exactly. You find out which one's the smallest number and divide everything by the smallest number. And then you cross your fingers and hope that turns out to be a whole number. Well, in this instance, it is. If I divide both of these by 2.27, I get 1 mole of carbon and I get 2 moles of oxygen. So what's my formula for my compound? 1 carbon, 2 oxygens. Good old CO2. And that's what it is, because when you ferment something, like if you made beer in grad school, it's fun. You should try it sometime. It's a lot of fun. You put a bubbler in the top. Basically, you don't want any more oxygen to get in there, and so you plug it, but you have to let the CO2 be released, and so you get these bubbles of CO2. So depending on where it is. I think I had mine in my room. You just like wake up in the middle of the night with a big boom coming of CO2 being released from your fermentation. So that is one of the products that is released as a gas, and the other one is ethanol, which stays in solution. All right. So I think I'll wind up there. We probably won't get through. Obviously, we're not going to get through all of 6 by next class. So there's going to be some parts of chapter 6 that won't be on the test. So don't worry about that. If it's something that we haven't done before, it won't be there. I'll double check and make sure that there's nothing new. I don't think there is. I think the next chapter deals with some stoichiometry of reactions we haven't dealt with yet. But I don't think there's anything in chapter 6 that we haven't come across before. But if there is, I will leave it off the test. So any questions before we go? Man, everyone's tired today. It's a rainy, quiet day. All right, so my groups, I will see you this afternoon at 1:10. And basically, we're just going to be starting our review. And on Thursday, will also be a review session. So you want to get started on the recitation. Basically starts all the way back in chapter 3. Chapter 4, 5, and 6. So it gives you sort of a good indication of what sort of questions are going to be on the test. Okay? So
Okay.
I'll see you then. All right, I'll talk to you soon.